Hi everyone. In this video we're going to look at acid and base strength. So hopefully at this point you've looked at and you've sort of gotten familiar with acids and bases, just common ones like HCl or HBr, bases, sodium hydroxide, ammonia, and we're going to look at what makes an acid a strong acid versus a weak one and a base as well. Alright, so if we're able to split apart a covalent molecule or an ionic compound, we've called this dissociation. So we looked at this in chapters looking at how a solid would dissolve in water, looking at solutions. It's sort of the same idea in that when a strong acid dissolves in water, 100% of the acid dissociates into ions. So we get this single reaction arrow, meaning all of the HCl reacts with water. Acid, there's your base, okay? It loses a proton, so there's your conjugate base, okay? Water acts as a base, and you get your conjugate acid. So if you need review of this, look back at the previous video. All right, but remember, the more we have of hydronium, that is acid. That's what that is. Remember, H plus, H3O plus. So if we convert everything to H3O plus, then this is going to be strong. Okay, there's no equilibrium here. There's just one single reaction arrow. So we use that single arrow because the product is greatly favored. So products are greatly favored. All right, these are great to know. One thing I tell my students is if you know the acids that are strong, then there's hundreds of acids, but if you know the strong ones that are considered to be strong, then any of the other acids that you see, you know that they're weak. Okay, so if you look here, HI, HBr, HCl, so sulfuric acid and nitric acid, so good ones to know there. Okay, so for a weak acid, this is the opposite. So not all of the weak acid, only a small fraction of the acid actually dissociates, breaks apart into ions. Okay, therefore we use unequal reaction arrows because the reactants are actually favored in this situation. So here, this is acetic acid. It's considered to be weak, and so some of it will react as we've seen. We donate a proton right to the base there. Okay, it becomes H3O plus. So there's the base and its conjugate acid. There's our acid and conjugate base. Okay, but only a small fraction will do that, and that's the difference between a strong acid and a weak acid. So we have some common weak acids. A lot of students think HF is considered strong, and it's actually considered weak. Phosphoric acid, hydrofluoric acid. Okay, so then we've got our carbonic acid. Okay, and another one there. So if you see the unequal reaction arrows, like those equilibrium arrows we've seen previously, then that means you have a weak acid. And notice that we're looking at these in water, how they dissociate in water. So if you look at this on a molecular level, on the left there you see that the HCl breaks apart, okay? And so you form hydronium and chloride. So if you look back at our reaction, that's what we formed, right? This here. So that's what you should see at the molecular level. With a weak acid, if you notice, majority of what you're seeing is the acetic acid. That's a reactant, right? Okay, and so majority of what you're seeing here is acetic acid. And then there's your hydronium, so there's a few. Okay, but the less, notice here, you have less H3O plus. So the less hydronium you have, the weaker the acid. Okay, so the more that the acid dissociates and forms H3O plus, or the stronger the acid. Okay, because that is the definition of an acid, is how well will it dissociate to form hydronium. Same idea for a base. If you have a strong base, you see that single reaction arrow. It completely dissociates into its ions. And in this situation, water is going to act as the acid. And here's your base. And so a base gains a proton. Okay. And so it completely dissociates. Okay, so excuse me, backtrack here a second. So it completely dissociates here, meaning that it's going to break down. So if you look here, NaOH, all we're doing here, when you dissolve it in water, it becomes this. Okay, so here's two common strong bases. And then the same idea for a weak base. So it dissolves in water only a small fraction. So if you see those double arrows, that means that majority of it is going to be in this form, and a little bit of it will, the NH3 will gain a proton there, and the base will, or excuse me, the acid will lose a proton. So here's your base and your acid. Okay, so it gains one. We saw this in a previous video, but that is the difference there. Alright, so a strong base, you notice that you see lots of these hydroxide molecules. And for a weak base, you only see a couple, and the rest of it is your reactant. Okay, so it's not dissociated. So the more that an acid or a base dissociates into its constituent ions, the stronger that it is. If it stays intact and it doesn't dissociate, then the weaker it's going to be. Okay, and so it's just a good idea to have a general idea of what's strong, what's weak. So HCl, the reason that it is a strong acid is because it readily donates that proton. That's the definition of an acid, is that it donates a proton and it forms a weak conjugate acid. Okay, and so what I want you to see here is that if you have a strong acid, think about your conjugate acid base pairs, it forms a weak conjugate base. So they have an inverse strength relationship. Okay, if you have a strong base and you look at its conjugate acid, so it gains a proton, that's what bases do, acids lose. Okay, then if you have a strong base, it's going to have a weak conjugate acid. Okay, and the reverse is true. If you have a weak acid, then it's going to have a strong conjugate base. Okay, so they have an inverse relationship. So our conjugate acid base pairs, they have an inverse strength relationship. Strong acid is going to form a weak conjugate base. If you have a strong base, it's going to form a weak conjugate acid. So we can see this in a table. So this will be a nice table you may want to keep handy. Okay, if you have, so here's a strong acid. Okay, notice that its conjugate base is very, this is weak, this is strong. Strong, and this is weak. Okay, so I encourage you to look at these closely. I'm not going to talk through every single one of these, but it has these in order of strongest acid to strongest acid to weakest acid. And then over here, okay, it shows the conjugate base. So if you, conjugate base is when we lose a proton, right? Okay, so it shows that conjugate base, and then it shows that it's weak. So if you have a really strong acid, it has a really weak conjugate base. Okay, and so I encourage you to go through all of these and be sure you can draw them out. Okay, hydrobromic acid's next. It loses a proton if you look at its conjugate base, because that's what acids do. They lose protons. And so it's also considered weak. Okay, so if you have a strong acid, has a weak conjugate base. If you have a weak acid, then it has a much stronger conjugate base. So if we look here, let's look at the ammonium ion. Okay, this is considered to be a weak acid. And so if you think about it losing a proton, it becomes NH3, neutral, because it lost a positive charge, lost that positive charge. And so now it's a strong conjugate base. Okay, so what I want you to see here is the inverse relationship. If you have a strong acid, it has a weak conjugate base. If you have a weak acid, it has a strong conjugate base. And start to become familiar with which acids are strong and which ones are weak. For our course, we will use, we won't use anything that's not on this table, or very common acids and bases. All right, I hope this helps. I'll see you soon.